Right, welcome back. So, for today's main seminar, we have Akshara Prasad from the University of Göttingen, who will be talking about dynamical comparison and type semigroups. Take it away.
I should unmute this somehow, right? How is it? Hello? Hello? Is it fine? Hello? Can you hear me? Hello? Yes. Good. Okay. Yes. Thank you, Ben, for the introduction. And thank you very much, Aaron, for hosting me. And also, I should thank Karen, I suppose. This is my first time in Prague, and I'm quite happy to be here. I've been walking around the city. I quite like it, and I've decided that I would like to be invited many more times. Yes, so today I'll be talking about joint work with Bartosz, Hannes, and Jian Chao about dynamical comparison and type semigroups. This talk will be quite elementary, especially given that Aaron explained many of the concepts that go into this. But if you have questions at any point, please stop me. At some point during my talk, I may use the words Fisher algebras and groupoids. But if you don't know what these things mean, really, don't worry about it. They're not crucial to the talk. Yes, so yeah, maybe just to fix the notation in the beginning. As Aaron said, I'll consider groups acting continuously on topological spaces. My groups will be countable and discrete, and my spaces will be compact and multifaceted. And 5 minutes from now, I'll assume that all my actions are minimal, but for the first couple of definitions, that's not required. Yes. So if I have such a dynamical system, a group acting on a metric space, you have different ways of comparing subsets of X. And this can be useful as to know when you can compare subsets of X. And that is what dynamical comparison does. So if I have a topological space X, and I have, let's say, a closed set A and an open set B, when is A dynamically smaller than B? This is the notion that is central to my talk. So if you can cover A by open sets, let's say like this, and you can move these sets over using group elements inside B. So you apply the group action and you move this to disjoint sets inside B. Then I say that A is dynamically sub-equivalent to or smaller than B. So this makes sense, right? So you cover A and you move this around by this group action. So there are so if these are UIs, then these are GUIs. So there are different. So this is a finite cover. There are finitely many group elements that move this open cover to something that's inside B but disjointly. And so this is dynamical sub-equivalence. Let me write that down. What's a nice way to write this? And also maybe another notation, I will denote by O or O of X as a topology on X. And maybe while I'm at it, I'll also denote by mg of x. This is in line with the notation Aaron used. These are the G invariant Borel probability measures on the topological space. G invariant Borel. And as Pishan pointed out earlier, these turn out to be regular. Right on. Yes. Okay. So here, an action like this, and A, B as open sets on X, then this dynamical sub-equivalence relation, this was defined by David Kerr. So here I said A is a closed set and B is an open set, right? If A was an open set, how would you do this? If A was instead an open set, you consider any closed set that's inside A. And if you can cover them up by finite cover and you can move them around by group elements inside B like this, then you say that A is dynamically smaller than B.
Obviously, that's transitive. A is not B and B is not C, that is positive.
Yes, you can do that. Yes. That's a good question. This will actually be relevant when I define a type semigroup using this thing. Yes. I don't know how obvious it is because especially later I will consider multisets. There it becomes a bit more trickier, but it works out. It is transitive. Yes. Yes. So, and I'm writing compact, but I'm in a compact metric space, so any close set. Um, uh, does the definition make sense? Okay, so this is the notion of sub-equivalence I work with. So how can I define the notion of comparison for the dynamical system? Now, obviously, if you look at this, if there was some measure mu such that mu of A was greater than mu of B, then that cannot happen, right? Because you're covering A by finitely many sets and you're them to something inside B but disjoint A, right? So this cover will and these are G invariant, right? So sorry, I mean, you're moving by group elements. So this would mean that the measure of B is greater than the measure of A. So if this happens, then A cannot be dynamically sub-equivalent to B. So the obvious notion would be if A is smaller than B for every G invariant Borel probability measure, then if A is dynamically sub-equivalent to B for any open sets A and B in X, then the system has comparison. Right. So if the measure of A was greater than the measure of B for any measure, then this cannot happen, as that will make the measure of B greater by this GIUIs which are moved. And here there's not less than or equal to, because if the measures are equal, it can be a bit tricky. Like it can be sub-equivalent or not. That is a case by case study. Yes, so this was the definition of dynamical comparison introduced by David Kerr. And the reason he introduced this was as a dynamical analog of strict comparison for sister algebras. So if you have a dynamical system, you can construct its cross product, which is a sister algebra. And in the classification program of sister algebras, there's this Thomas-Winter conjecture, which says that three adjectives are the same for classifiable sister algebras, like strict comparison, finite nuclear dimension, and Zeb stability. And a very classic way to solve problems in sister algebras is to look at dynamical systems, cross products. If the problem can be solved for cross products, then maybe it can be solved for sister algebras, and the same method can be extended. So David Kerr introduced dynamical comparison as an analog for strict comparison, tower dimension as an analog of nuclear dimension, and almost finiteness as an analog of stability. But it's okay if you don't know what all these words mean. I also don't know what all these words mean really well. Yeah. So the question is whether all dynamical systems have comparison, right? And well, that is not true. There is an example by Ara and Rui Excel where they construct a non-minimal action on a totally disconnected space, which does not have comparison. But usually, people who study this, they only consider minimal actions and also minimal amenable actions on compact metrizable spaces. So it is still an open problem whether every minimal amenable action of a countable discrete group on a compact metrizable space has comparison. We still don't know of a counterexample. Yes. And what I will talk about in this talk is to kind of translate this problem from the dynamical setting to an algebraic setting in hope that it would make it easier to tackle this problem. And that is what I do with type semigroups. Before I define type semigroups, I would like to talk about a result by Narishkin, which says that if you're in a dynamical system, you have this comparison to measure. So what he shows is that, yeah, if you're like this, if you have A and B, if you have A and B such that measure of A is less than measure of B for every such measure, what he shows is that you can always chip away a small part of A that has measure less than epsilon, and the rest will be dynamically subequivalent to B. So you can cover the rest by open sets and inside B for any epsilon. He shows this. And this does not translate to A being dynamically subequivalent to B, but this is almost that, right? So this is comparison up to measure. And this is a really strong result. And I'll just go through the steps a little bit, give you a vague idea of the proof because it's an excellent proof and also quite elementary. Like you don't need strong technology to prove it. But also the weird part about this result was is that it's not written explicitly in any of Narishkin's paper. Like he has a paper that's like 7 pages long in Annals, and he's trying to prove something else in a lemma, and in the proof is hidden this result. And this is really strong. Yeah, so I just tried this down. Minimal means that there are no non-trivial G-invariant open subsets. So I'll write this. What I mean by this is that mu of A is less than mu of B for every G of X. And this makes it easier for me. I don't have to write this every time. This is also called the rank map, if anybody knows that, and it's also an open problem if every rank comes from measures. But yeah, that's not important now. Okay, so if you have sets like this, then and for every alpha greater than zero, then x is greater than 1. This is exactly this, but in a minimal setting, and you don't push around everything in A, but almost everything in A. So the way he goes through this proof is really nice. Mm, Even though there I've written A is closed and A is closed instead of open, that's just a technicality. It doesn't make any problem in applying this result. Uh, the way he goes through the proof is like this. So you have A, you have A and B, right? And if A is less than B for all measures, then we can find some epsilon such that this happens, right? So if B is greater than A with respect to all measures, there is also some epsilon such that this still holds. So what he does is he enumerates group elements in whatever order, G2 and so on. And he first applies G1 and moves A around. So suppose this looks something like this, let's say, and this is G1, A1. So this thing you have here, because we are in a metric space, we can just like enlarge it a little bit. Like you take the epsilon neighborhood of this. Yeah. So you have this G1, A1, and you intersect it with B. Sorry, A1 is A. And you cut out B, you cut this part out from B, and then you move this back with by G1. So you have something more here, let's say, and you cut this out from A. So in the first step, so he runs an induction process and algorithm in which in the first step he moves around A using some group element and he enlarges just a little bit in B and he cuts that out from B. He moves it back to A, he cuts that out from A. So you are left with a subset of A and a subset of B. And he does this in such a way that this new subset of A, so let's call it A A1 and the other is B1. He does this in such a way that you still have this. This is a technicality, this needs some calculations, but yeah, you can do this. And then from whatever remains, so what remains after this is you have like something like this, right? You have something like this. Right? And then he moves this around with the next group element. And let's say, I don't know, it comes here or something like that. He enlarges it just a little bit. He cuts that out from B1, and then he moves it back using G2, and he cuts that out from A1. So you're left with an even smaller set. So yeah, so you can run this induction process, and because the system is by doing this, you definitely end up with disjoint subsets. So yeah, I'll just write a few words. Uh, right. And these are nested sets, right? So you can take, say, A infinity to be the intersections of all these AIs, and B infinity to be the intersection of all these BIs. And then because this system is, you have G infinity intersection B infinity is empty. And then what it shows is that this can happen only when A infinity is a null set. Uh, yeah. So that means you are like shrinking A up to the null set. So at some point, you have some A n that has measure less than epsilon. And then there's also a way in which he covers these remaining things. So at stage AN, you have measure less than epsilon, and then the rest is covered by open sets, finitely many open sets, which can be moved around into B1 or Bn. Yes, this is the technique of the proof.
Again, identity makes sure that these sets are strong.
Yes. So if you did not have minimality, this could also be disjoint way earlier. You wouldn't have to run through the group elements, and also this. Okay. So I said A is closed, but it could also be open. And if this was still the case, then you have an invariant set, right?
But I thought what you need is that these sets that you move into B, they are all disjoint.
Mhm.
I don't see how that. Like even in the second step, like you have this first set that you cut out, like G1A that you cut out of B. How do you make sure that if you take G2 of A1, that that is disjoint from G1A?
Yeah, that's a good question. Yeah, so there's some technicality involved there. Like the way you construct these ANs and BNs, it is this construction involves you getting disjointness, and the way you can move this around and still get this disjointness, like kind of at each stage, but not really, that uses minimality. Yeah. Yeah, it is not so straightforward, but you wouldn't get this without minimality. Yeah. I mean, maybe you could impose some other condition on A and B to get that. Maybe something like GA is contained in B initially. If this was an initial assumption, maybe you can get it, but I don't know. Yes. Okay. Now that this is out of the way, I would like to go about defining the type semigroup. Yes. Okay. So first, I will be using this f of whatever. This is the free commutative monoid generated by the topology on X. So yeah, maybe I should explain this a little bit. So my point with the type semigroup is to translate this problem to an algebraic setting, right? So I want to be able to add these open sets and still compare them. But this adding of open sets should still somehow respect this dynamical sub-equivalence relation. So it's not enough to just take the unions of open sets. You kind of need to consider multisets and still be able to compare these multisets with some other multiset. If you know the language of full semigroup in C-sharp algebra, this is basically what you do. You don't just have elements, you have these elements in the stabilized version, and then you want to compare them, right? That is basically what we want to do here with the type semigroup. And in fact, the type semigroup is is a dynamical analog of the Kuhn semigroup. I'll explain more of this later. And it's okay if you don't know what a Kuhn semigroup is. Okay, so I define this free commutative monoid on the topological space. These are exactly the lower semi-continuous bounded functions from X to the natural numbers. Yes, and you have an order on this by the usual pointwise dominance. Yes, okay, and the type semigroup will be a quotient of this algebraic structure. And to define the relation with which I take this quotient, I need some other relation, which is called the way below relation or the compact containment. So, yeah. So in lattice theory, there's this notion of way below compact containment, and I'm not going to define what that is. But in this case, for f of O, this ends up meaning that k bar is less than or equal to f. And what this means, if k is written as sum over one of ki's, then k bar is sum over one of ki closure. So this is kind of what you have here, right? So you take a closed set inside of A, and you can, yeah. So this is the, so here I had an open set A, and I'm considering closed sets inside of A, right? That will be a way below set or a way below function inside A. And if you are considering multisets that are these functions, indicate some finite sums of indicator functions, then you get something like this. Does it make sense so far? Any questions? Okay. Now, I want to translate this relation here to a relation on functions here, right? So just like I have dynamical subequivalence there on open sets in X, I want a dynamical subequivalence on functions in f of O. I just write f of for f of x. If instead of finite sums of indicator functions, you just had one indicator function. So suppose if f was just 1 over u and g was just 1 over v, then this exactly means that you're taking a closed set inside A, and you're able to move that around. So you have an open cover on it, and you have finitely many group elements that moves this open cover to something that is disjoint in the support of G. So this is precisely that notion, but adapted to multisets.
Yes, sorry, can I ask where's the disjointness reflected?
This is exactly because you're taking indicator functions, right? And this need to be inside G. So if G was just V, let's say, so if the support, so if G is just one V, then because these are indicator functions, they need to be different. If they were overlapping, then at that point it has value greater than G's value, right? Yeah. Yes. Okay. So if this holds, then I say F is dynamically below G. And I consider the equivalence classes I obtained from this relation. And that forms the type semigroup. So if F is dynamically subequivalent to G and G is dynamically subequivalent to F, then I consider them to be the same in this type semigroup. And by this exact relation, this relation descends to a relation on the type semigroup, and it gives you a partial order. And you can also form sums of elements the usual way. Yes. Yeah, so as I was mentioning earlier, the type semigroup is a dynamical analog of the Kuhn semigroup for positional algebras. And the reason we define this type semigroup using functions instead of just multisets is so that this type semigroup mimics the Kuhn semigroup. This allows us to have a map from the type semigroup to the Kuhn semigroup. It's not a very interesting map, but it exists. If we define the type semigroup in a different way, which is possible, that could potentially destroy the relation to the Kuhn semigroup. Yes. And if you know anything about the Kuhn semigroup, you know that it's very important to the classification program, and it encodes a lot of information, but it is notoriously difficult to compute. And the goal with the type semigroup is to construct something that mimics the Kuhn semigroup, is easier to compute. And of course, it will encode slightly less information, but if it encodes precisely the information we want to check, then that's good enough. And here we want to check when a system has comparison by looking at its type semigroup. And the result is that a system has comparison if and only if the associated type semigroup is almost unperforated. I'll define what this means. Any questions so far?
It's trivial. How is this related to the objective consent group?
Yes, so if you're taking C0 of X or something like that, that's what you're saying, right?
So it is just the same.
No, it is still not.
It's still not.
It's still not, yes. I mean, they end up being the same in very few cases, like the simple purely infinite case, for example. But yeah, but
Cases.
yes, yes. But that's the uninteresting example of the Kuhn semigroup. So the Kuhn semigroup and the type semigroup is zero infinity in that case. Yeah. Okay. Now I will write down Narishkin's lemma in the language of type semigroups, which will be useful for me improving the main result later. So this exactly means that I'm taking a closed set inside U, right? Like how it is there. And U is measure-wise smaller than V. Then for every yeah. So that is exactly this statement written there in the language of types and groups. So you're covering U prime, this closed set inside U by open sets, one of whose measure is as small as you want it to be, and the other is dynamically sub-equivalent to the bigger set. Okay, now this helps us translate dynamical comparison from a system to comparison in the n-fold amplification system. Is it better if I move this up? Can you see it if I write it here?
Sweet.
Yes. So this n-fold amplification system is G times the permutation group on n elements acting on n copies of X. So using Naрешkin's lemma, if a system has comparison, if a minimal system has comparison, then that would imply that this n-fold amplification system has comparison. And if you see where I'm going with this, you'll notice that this n-fold amplification system gives you, like, let's say compare multisets, right? So you have in the n copies of X, you can take different open sets. So you can take U, UN, so you have tuples in this X, the n copies of X, and you can compare this with some other n tuple using comparison. And this is kind of the relation you have in the type semigroup. And this was not known before. And this, like the Naрешkin's lemma is crucial to proving this, at least in the way I know how to prove it. Okay, so first of all, every measure on this n-fold on this n copies of X comes from a measure on X. So every mu in Q of X measure same mu. So if you take an n tuple in this, then you can define it to be the weighted average of the measure of not the weighted, just the average of the measures of each of these sets. So this will be And what's more is that every measure on this comes exactly like this from a measure on mg of x. This is because we are considering only Borel probability measures, right? And that can happen only in this way. Yes. Okay. So now I want to verify comparison in this n-fold amplification. So I need to take two sets in this n copies of x that are where one is measured by smaller than the other, and I need to show that one is dynamically subequivalent to other, right? So and I want to now show that U is dynamically subequivalent to V. So to do that by where is this? So by this definition, I need to consider a function. Oh no, I need to use this definition, right? Yeah. So I need to consider a closed set in A, which in the language of type symmetry is exactly something that is way below U here. So to show and I need to move this around using group elements to something inside V. Okay. By the way this way below is defined, you can always find some other set that is in between these two things, but is still way below the other one. That is, there exists U double prime with U prime. Yeah. This you can always do. This is sort of the continuity of f of O with this relation. Yeah. Okay. Now we have the measure of U is less than the measure of V. That is, we have mu of U1 plus mu of UN less than mu of V1 plus mu of Vn for every mu, right? So you can consider that the first one, let's say V1, is non-empty and it has positive measure. So as a V1 is non-empty, so it has positive measure. So I can shrink it just a little bit and still have this relation. So I have let's say this is V, and I shrink it just a little bit. I get V1, and I can do this in such a way that the closure of V1 is still strictly contained in V. And because I'm in a compact metrizable space, I can find open sets all over here. I have not a lot of time, right? Maybe like 15 minutes. Oh, that also includes questions, I suppose. Okay. Okay, I'll see how fast I can go through this. Yes. Okay, wait. So since the rank of u, like u, the measure of u was smaller than the measure of v, and u double prime is way below u, you also have the same relation for u double prime, right? So you can still do this thing because each of the ui double prime is contained in the ui. Uh, yes. So now. Use and because these are all non-empty and they lie in this hollow this complement of v1 prime that is created, you can find an epsilon such that the measure of each of these sets is greater than this epsilon for every measure. Yes. Now I want to apply Navish-Kin's lemma to the data there. And what I'll basically do is I'll move most of these UI double primes inside these WIs. And these will have measures smaller than epsilon, right? And the rest I can cover. That's the point. Rest things here. I will apply this corollary to the data here. So this is the open sets in n copies of x, such that you have u prime contained in this tower, right? And y is dynamically sub-equivalent to v, and uh, z is less than epsilon. So yeah, so each of these zi's, I choose them small enough because by the corollary we can find them to be as small as we want, right? So I choose them small enough for an epsilon, and I move each of the zi's inside the wi. And y here is smaller than is dynamically sub-equivalent to v. I can move y inside or v prime. Yeah, so I'm moving. Yeah. I have U prime here. I'm covering this. So this is Y and the rest is Z. So I'm putting each of the Z's inside the WI's and I'm moving the Y inside this. So Y goes inside here using Narishkin's lemma. Yeah. Yeah, I could go into a bit more detail here probably to make it easier to understand, but I'll get to my main results now. Yeah, so I said that dynamical comparison of a system is equivalent to the associated type semigroup being almost unperforated. So I need to define what almost unperforation is. Uh, if you take any x and y in any p-ordered abelian monoid, for us it's the type semigroup, and if there exists a natural number n such that you take n plus 1 copies of x and you can put them below n copies of y, then if so this is sort of a stable domination, right? It's also the same almost unperforation you have for semigroups. So you kind of amplify these elements, but you amplify x just a bit more than you amplify y. And if you have domination there, and this implies the usual domination, then you say that the monoid is almost unperforated. So this means that it has like no gaps, almost no gaps. Right. Okay. And um, let me say a couple of sentences about this result. So there exist similar results in the literature already. For example, Shinma proved the forward directions. Like he proved that if a system has comparison, he proved that if the type group is almost unperforated, then the system has comparison. And this result was already known. Like this equivalence was already known for actions on totally disconnected spaces. But this is more general. We are not assuming the space to be totally disconnected. And this also proves the implication in both directions. And this kind of readily follows from the previous lemma there. So for example, like go from almost unperforation to comparison, that's Shinma's result. For the other direction, if you have a system with comparison, then you can go to its n-fold amplification system that will have comparison. So to prove almost unperforation, you take F, G in this implies F is less than G, right? So, but this, it's in this n-fold amplification system. And there you'll have this. This would mean that if F was written as 1 over ui, let's say, and G was written as 1 over vi. This would mean that mu of u1 is mu of un is less than mu of v1 is mu of vn. And this, by comparison, would imply that Vn, right, from the previous lemma. And this is exactly F and G, yes. So this is the result. Yeah, and maybe I should stop here. I would like to show an example, but yeah, maybe I stop here. Thank you.
Questions for Akshara?
Maybe two questions. So maybe this is silly, but you said that you defined almost unperforation. So just unperforation.
Sorry?
I see that word. Just unperforation.
There is unperforation, yes. It exists in literature, but it is also almost never used. I can try to recall what it means, but there's a chance that I get it wrong. I think it means that if n x is less than n y, this means x is less than or equal to y. The point is in pre-ordered abelian monoids, you don't have cancellation, right? So you cannot take like this minus x or something like that. There's no minus, so you don't readily get this. So I think unperforation means this, but I could be wrong. Yeah.
And the other question was, does this have something to do with the cross product of the actual? So does the type semigroup of the actual, is that connected to maybe the concept?
Yes. That's a very good question. There exists an order preserving additive map from the type semigroup of the system to the semigroup of the cross product, but that is it. Like this map need not be injective or something. So there is something that preserves some order, but not very well. And as I mentioned earlier, David Kerr introduced this as an analog of strict comparison, right? So the hope was that maybe dynamical comparison implies strict comparison and the other way around. But it has been shown by Narishkin that for cross-product dynamical comparison doesn't always imply strict comparison. But one of the ways we can apply this result to cross products is we know in classification that in some great generality there's a dichotomy between pure infiniteness and stable finiteness, right? And you sometimes need an assumption like strict comparison to have a dichotomy like this. But here, even though dynamical comparison doesn't imply strict comparison, you can get a dichotomy for cross products using some results I have with Bartosz and Ralph, where when you have a groupoid whose type semigroup is almost unperforated, then its Fisher algebra admits this dichotomy in some other assumptions. But yes, so this is one of the ways you can use it.
Thank you.
Can you say again what you assuming about the group G?
Countable discrete. Yes, good question. So I'm not assuming amenability. I'm also not assuming amenability of the action. I should have mentioned this. Thank you. So Narishkin's lemma actually assumes amenability of the action, but he only assumes it to cite some other result of Kerr and Szabo in his proof, but that also doesn't really need amenability. That can easily be removed. So this result doesn't need any amenability. Yes. Yeah, and while I'm there, I would also like to say that another use of this result would be to take some ordered monoid that is very weird, so that is not almost unperforated, and if you can associate that to a dynamical system, then you go from a weird result in monoid theory to getting a dynamical system which does not have comparison. And such monoids exist, and they have also been related to dynamical systems. These are results by Veru, and like the results like it seems that it really implies that you can find a minimal action of a group on a totally disconnected space even that does not have comparison. But we don't know anything about this being amenable or not. So this could still be a nice counterexample, and the results that are required to prove this already exist, but like nobody has ever put them together. And like type semigroup doesn't really see amenability of the action. This is a disadvantage. Yeah.
But you're saying there's some machinery for realizing given monoid as the type semigroups of some dynamical system.
Yes, not any given monoid. You take a conical refinement monoid, countable conical refinement monoid. Yes, I think such monoids can always be realized as the type monoid associated to an action of a group on a totally disconnected space. Yes, this is a result by Verum.
Yes, since you were running out a little bit of time, maybe let me ask the question. So, can you show an example?
Thank you so much. This is my favorite question. Uh, so I'll show the example of the irrational rotation. So I take the integers acting on S1 by irrational rotation. So theta is an irrational number. I hope everybody knows what this is. So you have nz equals what is equal to z. Right. And if theta is irrational, then this action is minimal and it is uniquely ergodic. So there's only one gene variant measure and it is ergodic. It ends up being the normalized Lebesgue measure. So yeah, so you have S1, right? So how would its type semigroup look like? So if an interval is contained in the other, so for example, if this is and this is contained in A prime B prime, then so these are the open sets in S1, right? That is what goes into making f of O. So you can readily see that A, B, this will be dynamically below this A prime, B prime because it's already contained. And even if you can move this around, so if there is some other A double prime, B double prime, such that you can move A, B such that it is inside this, then even then this interval is dynamically below this bigger interval. So what this shows is that so among all these open sets in S1, this dynamical equivalence relation happens only when the length of the arcs are the same. So if the length of an arc is smaller than the length of another arc, then this is dynamically smaller than the other. If they're the same, then they're dynamically equivalent. And we also have this entire set S1, right, which is Klopen. So this type semigroup WZ of S1, this actually ends up being and disjoint union 0 infinity. So for example, so you have so this if this is 1, this is 2, so this will be the element S1. This is not dynamically smaller than any other thing, right? It is only dynamically smaller than itself. But the type semigroup, you can also take multiples of it. So this would be 2S1 and so on. But there are also these arcs inside. So you have, so those will relate to, so 0, so this is 0 and this is infinity, so on. So you have something like this. Maybe let me write it a bit better. Yeah, so yeah, so these things here, these are like the compact elements. An element in the type semigroup is said to be compact if it is way below itself. And in this case, it can only happen when it is S1 or its multiples. But the other elements, they're soft elements, which means they're not way below themselves. So here, so this is 0 infinity, I said, right? So a number here related to the length of the arc. And the dynamical relation between these two are like this. So if this is 1 here, so 1 would be, for example, the sum of two semicircles, right? So everything here is dynamically below this. And these are just multiples, right? So you take like sums of arcs. And everything here will be dynamically below 2s1 and so on. And here there's the usual dominance, and here also there's the usual dominance. So this is what the type semigroup will look like. And this, you can see that this is almost unperforated. So if you have n plus 1 of some number here, which is smaller than n times some other number, that would immediately mean that the number is smaller than the other. That means, so this type semigroup is almost unperforated, which by this result means that the system has comparison. It was already known that this system has comparison, by the way, but this is a small example that shows this from type semigroups.
Can you include 0?
Yeah, 0 is the null set. Yes. So 0 is in here. Sorry. Yeah.
So this is this is like the unstabilized consent group.
This is exactly. Good question. I should have pointed this out. I used W for the type semigroup to denote that it relates to the unstabilized consent group. Yes.
But this is specifically of the chance of this. It's
right. In this case, it coincides. Yes.
It's coincidence. So
I mean, so this is an example where the type semigroup is encoding all the information that is also encoded in the Kuhn semigroup. But I don't know if it's a coincidence or there is more. Like,
did you say the Jackson?
yeah,
This will give us another.
yeah, this is the non-commutator. Yeah.
no, I'm saying that this group that is not is the unstabilized consent group of the council.
Okay.
Wondering about
I don't know the relation between this and Jiangsu algebra. Okay, you're saying this is also this.
Yes.
Oh, I cannot tell you anything about that.
And then this is second of the 12.
Yes, this is. I think it is.
I guess so. I mean,
Yeah.
it's just about that the K0 group it's just unique trace. I guess why that is. That's what you mean.
I mean, if the Kuhn semigroup of some C-star algebra is isomorphic to the Kuhn semigroup of the Jiangsu algebra, can you tell anything about this C-star algebra?
Yeah, that's not.
Yeah, it's a similar question here, right? Yeah, so I don't know.
This method is a lot of the goal.
Any questions from the audience? Yes, I think,
Going over this directly.
see you all next week for talk by Valentina. Charles.